welcome back, everyone. So hope you've had a nice break, had a nice lunch, some nice discussion. So the final speaker of the conference and today is Mark Richards. So Dr. Mark Richards is a senior teaching fellow at the Department of Physics, Imperial College London. He first obtained a BSc in chemistry from Manchester and then a PhD in physics from Imperial College London. In 2019, Mark was formally elected a Fellow of the City and Guilds Institute of London, so the FCGI, in recognition of his unwavering support to education and training of young people. So if you don't know Mark, he has many interests. So he is also a co-founder of DoVAS Technologies, so it's an Imperial spin-out specializing in wireless air sensing networks for real-time pollution mapping. And he also has a lifelong interest in music as DJ Ken. So Mark, the floor is yours.
Thanks. Thank you very much. Okay, good afternoon, everybody. It's an honor to be here. Firstly, I didn't realize I was the last speaker of the conference. That's almost like the relay race. You know, it's the last stretch that actually counts, that gets you over the line. So no pressure, I suppose. But yeah, thank you for that warm introduction. As he said, I'm Mark Richards. Maybe just to put myself into a little bit more context, I'm currently at Imperial. I'm also a deputy admissions tutor. I've had experience in industry as well as finance and other things, and a part-time DJ chemist, and also a founder of the Blackett Lab family, which is the UK-wide network of black physicists. So I'm very much coming here as a physicist, but of course, you know, there's plenty of maths in the physics, so all what I talk about is underpinned by the language of physics, which we call maths. Okay, I suppose just to give you a little bit more of a visual representation of where I'm coming from. I mean, I haven't changed that much since then. But essentially, I grew up in Nottingham. My parents came from Jamaica in the 60s, I suppose as part of the Windrush generation. And I grew up in Nottingham, went to a normal state comprehensive school. But essentially, the green sort of shows times that I've spent in industry, and the blue sort of shows times that I've spent in education and research. And the main thing I'm sort of saying here is that in terms of my career trajectory, I've kind of navigated different sectors, and I think it pays to be versatile, so to speak. So I'll give you a little insight into some of the research that I've been involved in. So I started off as an undergraduate chemist, and I suppose I started asking why too many times and ended up doing a PhD in physics. And I sort of proved by my own lived experience that physics is the fundamental science. And one of the things I was really interested in is how you can, I remember it was actually this spectrum, the spectrum of hydrochloric acid. I was in a chemistry lecture, and they was explaining this spectrum and what it all meant, and how these bands mean different vibrations and so on. And then I started to ask, well, why? Isn't that strange how you can use infrared, which is light you can't see, and you can shine it, let's say, through a gas like hydrochloric acid, which you can't really see as well. And then you've got a detector at the other end which detects this light, again, which you can't see. And all of a sudden you get this almost perfect image of how it behaves. So I thought, well, imagine you can sort of get visibility from just unseen things. And that was really interesting to me. And then I realized, of course, it was all underpinned by quantum mechanics and quantum physics. So I ended up doing a PhD in atmospheric physics, where they wanted to spectroscopically characterize different chemicals in the atmosphere, because at that time they were really interested in ozone depletion, and they wanted to be able to quantify the abundances of various chemicals which contributed to its depletion. So that's how I sort of got into it. And again, waves, if you like, are at the heart of it, in the sense that when you think about how light interacts with matter, then that is essentially what generates, the molecules can get excited and release this energy which we can detect. And effectively, I was interested in sort of how light waves interact with atoms and molecules, and how you can use that to characterize them, to quantify them, and so on. In atmospheric physics, You use the same technique to quantify atmospheric abundances, but you use a technique called satellite remote sensing, where this time the light source is actually the sun itself. And that gives this really long optical path. And if you have a long optical path, you can build up a large signal, which means that you can detect very small quantities more easier. It makes your instrument more sensitive. I don't have many equations in the actual slide, but this is one equation, or one particular equation which we relied on, the Beer-Lambert law, which basically it gives you an indication of the scattering and the absorbing features of the molecule. I don't know if this is a, oh yeah, there you go. And what we try to determine is this N, the number density of the, in other words, you know, the number density, the concentration, if you like, of the trace chemicals. And as I said, this long path allows you to really be quite sensitive, you know, down to parts per billion in terms of sensitivity. Now, when I returned to Imperial as a postdoc, they were interested, there was a project where we were interested in urban air pollution. And urban air pollution was very much a big issue. Well, it wasn't, in fact, it was a big issue in the research world, but it wasn't necessarily a big issue in public. But nowadays, every day you could probably get an article on air pollution. But at the time, in the early 2000s in particular, it's a global issue, and about 16 of the 20 most polluted cities were in China. And then later on, towards sort of 2016, and so 14 of 20 of the 20 most polluted cities were in India. And it sort of seemed to map with this sort of urban development and not quite understanding the dynamics between how you integrate urban transport and all those other things and map that with air quality. So, and again, when we talk about pollution, there are many different types of pollutants, even though we use a generic term, but in reality, you've got gases, which we can use the optical techniques I talked about to detect, but then you've got other things like aerosols and so on, which you might use a slightly different technique, for example. But I was involved in a project called MESSAGE, which wanted to correlate transport activity with air quality. And as you can see, if you sort of follow the flow chart, transport produces emissions, poor air quality leads to a poor exposure levels, high dose response, and eventually adverse health effects, which have both, of course, a social and economic impact. Okay, and so the idea was to sort of monitor and model transport, and at the same time measure air quality or air pollution sort of dynamically. So the idea was to develop sensors that could sort of be fit on vehicles and so forth. So in other words, mobile sensors, and then map that with sort of traffic incidents and so on. So what did we do? I suppose what was the innovative part is that we took this technique in atmospheric physics, but the problem is if you want to measure urban air pollution, you don't have the sunlight as a source, so you can't produce these long optical paths. So you're going to have to reduce the optical paths instead of several kilometers, maybe to a few meters if you're lucky. Okay, so you're reducing your signal by, say, a factor of 1,000. That would give you a very, very weak signal. However, I was actually based in the high energy physics group, and they did a lot of work at CERN where they look at high energy collisions of trillions of particles, really, and they may be looking for a few hundred which provide the signature of a new elementary particle. So what they've done in the process was develop these very robust noise reduction techniques to reduce the noise in the system. And so we figured that actually for our atmospheric spectrum, what we're really looking for are also weak signals in a noisy background. So we combined the two techniques really, this DOAS technique, differential optical absorption spectroscopy, with the noise filtering techniques from high energy physics to create our first sort of open path unit where you'd have one transmitter and a receiver across the road. And as a vehicle went past, you could sort of measure the emissions and so on. But of course, if you want to fit them on moving vehicles, even this open path unit is not sufficient. So we had to use the same sort of components, key components, the source, the optics, the detector, and then the algorithm that obviously does all the calculations and sends the data wirelessly. And so we then, instead of having an open path unit, we had a closed path unit, and we reconfigured the optics in a particular way, which allowed us to draw air in and still monitor air pollution. But this time we've got this sort of mobile unit. And some early iterations, this one in the middle was in a violin case, which you could sort of walk around with. I also tried to launch my modelling career at the same time. Obviously it didn't work because I'm here. But nevertheless, what we were trying to do was replace the, if you like, the capability of the traditional fixed air quality monitoring stations. And these are two examples. This is a large one here, looks like a large shed. This is essentially a mobile monitoring station, which also looks like a large shed, but it's got wheels on it now. And we wanted to replace all of that with something you could be much more agile with and get pollution on a sort of interrogate pollution on a street by street basis. And this is where we, in a very sophisticated way, strapped it to a vehicle and drove around so we could actually have some real-time mapping. And again, as I said, these were early iterations. Eventually, we moved from a violin case to a gun case. That was quite fun at the time. Not for me, but nevertheless, it was the most appropriate casing for the unit. Okay. But then the key thing was actually that we realized that this technology was exploitable commercially. It was always known as what was known as a technology transfer project, where you can actually, there are elements that are going to be useful in the commercial world. And eventually it culminated in forming a company called Duvas Technologies. And just to sort of put it into context, to get to this stage even, it required elements of atmospheric physics, of course, and chemistry, as well as optics, spectroscopy, gas phase chemistry, and so on, and computing and electronics. So it involves lots more than just the fundamental physics that it started from. So that became sort of a near to commercial unit. And then we go to the engineering phase. So now we have to bring in the engineers if you actually want to make it something that's usable and sellable. And so it went to a sort of engineering phase where we reconfigured the optics, and everything is still there, but we've reconfigured them in a much more productized way. And this was one of our researchers actually. I mean, it's not quite a fashion accessory, but you could almost get away with sort of measuring air pollution discreetly, so to speak. Okay, so just to point a little bit of the data that we found at the time. For example, this is a sort of campus of Imperial College. That's the Royal Albert Hall, the roof of it. And we drove around here, and you could see that there were large spikes in these corners here. Any idea why there would be large spikes in the corners?
Because you wait there longer.
No, well, partly because we wait there longer, but also because you've got junctions in both directions.
Density.
Okay, so yeah. So it kind of confirming what we thought, but nevertheless, it's nice to see it visually. This was an example where we had two sensors walking side by side, but then at one point, one went into the middle central reservation of a road, and the other one stayed at the curbside. And you saw the large difference between pollution in the center of the road and at the curbside, for example. And just to give you a sort of idea, around 100 parts per billion is actually the legal limit, but it's averaged over about 8 or to 24 hours. So that's why all these spikes get sort of spread out over 24 hours. So in a sense, but you can see the stark difference. It goes way above the legal limit, if you like. And this is one actually where we stood at a junction. And this is where you sort of see the pulsing of the traffic lights when they change. So we stood at the junction and just monitored it for about a 15 to 20 minute period. And if we average that out, it would come to less than the legal limit. However, if you, let's say you were selling newspapers on a street corner, you would be exposed to these sharp spikes periodically. And the physiology of the body is such that your body has a non-linear response to high dosage. So a high dosage over a short period of time is going to be far more damaging than that dosage sort of spread over a longer period of time. So things like selling flowers on a street corner, I started seeing them as quite a dangerous job. And then you see someone who's maybe near to retirement doing that kind of job and not realizing that you're actually putting yourself in a lot more danger than you probably realize. So it was useful to bring the data to life. And then, of course, we moved more to the stage. The idea really was to network these units so that you could create this network of sensors and create a sensor network. So this was some early work where we created some pseudo-synthetic data based on a scenario in East London at the time, where we had put about 140 sensors and said, well, if we could distribute them almost like a grid nice and evenly and monitor pollution continuously, what sort of information could we get? And so we visualized we developed some visualization tools, and we saw what we probably expected, that along the main roads, it's going to be polluted. This is a time at the top left here. So along the main roads, it's going to be polluted during rush hour. And then as rush hour dies down, then you'd expect that the pollution would die down, but you still see certain pockets that remain, for example. And then we started to look at specific areas, snapshots at different areas. This was one with a school, for example, where at 9 o'clock the school is polluted and the main road is, but at 3:30 the school's polluted, but the main road isn't. And at 5 o'clock the school's not really polluted, but the main road is. And just by working that out, you can see, well, actually, it's probably the school run which would have been contributing to that localized pollution in the school. So it's these kind of visualization tools which are really useful for local authorities. And then we started moving more towards thinking about not so much the sensors anymore, but more about the network, because it's not realistic to have a fixed network of sensors there. Just getting planning permission alone would be impossible. So the reality is, what if you had, let's say, if we could have the same coverage, but maybe with fewer moving sensors? So our first scenario was based on, say, instead of 140 sensors, we'd have 7 sensors moving in a kind of cyclical direction. And then using that same rich data set, sort of extracting what these sensors would pick up, and then visualizing that and analyzing that. And that was the first scenario. The second scenario was then taking sort of irregular paths and then collecting the data for that. And then finally saying, well, what about an ad hoc network like buses? So we only put the sensors on the bus route to get an idea of what information they would pick up. And the reason why we're doing that is to say, well, can we still identify the same pollution episodes we otherwise would have done with this rich data set? And so we did some comparisons. And the main, I suppose the net result is that these are the 3 different scenarios. This is the sort of static sensors on the left. This is what the mobile sensors would have picked up. And you can see that the hotspots and so on are pretty well represented. And we even sort of did a subtraction and looked at the residuals. And so the only issue with the buses is that obviously it wouldn't pick up any data in the areas where there are no sensors. But often those are the sort of fields in the areas where the pollution was low. So what it's really showing is that we can actually use much fewer sensors in a more mobile, agile way and still recover the vast majority of the data, which sort of led us into sampling theory. Again, going back into mathematics, because a lot of it was based on how you sample and the frequency and so on. We also realized, of course, that it has much more applicability than just air pollution. The technology, the platform technology can look for other things in the air, ranging from, could be a sort of biodefense type material, health and safety, for example, or continuous emissions monitoring and so on, industrial processing. So what that means is it opens up different markets in different sectors by tuning the instrument to look for those particular species. Okay, so one of the things, going back to my PhD, this was me with the Space and Atmospheric Group in Imperial. I know you're all straining your eyes, wondering where am I? I'm there, okay? I am here, that's it, yeah? Okay, I was trying to blend in. So the point I was actually making is when I sort of reflect on, there's many people in that group. So for example, former head of department, that's actually Michelle Doherty, who was recently named as the first female astronomer royal for the King, for example. We also had a former head of department, Joe Haig. We had, that was my former supervisor, became the scientific advisor, Welsh scientific advisor. We also had a former head of the European Space Agency, and I could go on to many different careers. But there's obviously a question in the back of my mind while I'm in this environment. Why aren't there more people like me in physics? And especially at places like Imperial. So I tried to rationalize it. As I said, I do like to ask why. And maybe I thought, well, because my parents, came over as a sort of Windrush generation. I'm sort of the first of this generation. Maybe I'm just the first of a wave that's on their way, and I'm just slightly ahead of the curve. But then when I returned several years later, I realized the situation was probably worse than when I left it, because I wasn't even there as a PhD student. So clearly, by simply waiting, nothing's going to change. And also, when you ask why, they say, well, there's not enough numbers applying. Why is that? Well, the pooling in the graduate is not big enough. Why is that? And so you realise very early on that the problems are much earlier in the pipeline in school, in schooling and so on, and education. And that's when I obviously got much more involved in outreach and trying to inspire young people. I'd always been involved anyway, but I realised that I almost saw it as a slight mission to try and do something to try and change this. And even at that time, I didn't really know any other black physicists at all.
Sorry, Mark.
Yeah.
I think there's another black physicist in the picture, right?
Yeah. Now, this is the funny thing.
Oh.
I only met him once, and then you got that photo. I'm being serious. That's all I can say. I'd love to know who he is. Yeah, I will. I've tried to do digging, but I don't know. Yes, I mean, I hope, yes. That's all I can say. That's why I didn't mention this person, unfortunately. But yes, I only met him that one time. Very pleasant, but I'm not sure because at that time I was a PhD student. I don't know what his role was at the time. Okay, but going back to research and thinking also about research and what we mean by inclusive research. What is research supposed to be? A body of knowledge, that's what they say. A record of human endeavour over the centuries and over the millennia. And also a global collaborative effort. No one demographic or group can claim the entire research sphere. But I'm going to take a few examples from my sort of discipline, physics, to show that is this actually being addressed or adhered to? So the first one is Satyendra Nath Bose. I don't know if anybody's heard of him. Has anybody heard of the Higgs boson? Yeah, well, it's named after him, Bose. Okay. Now, the thing about Bose, he realized that substances, when they get to very, very low temperatures, they can behave in a very different way, much different to gas, liquids, or solids. They behave in this very strange way because of quantum effects. And he tried to get his work published. He was let's say, a humble scientist from India, trying to get his work published. No one would pick it up. And eventually he wrote to Einstein and explained to Einstein, he basically said things along the lines, we're all students of yours, these are my thoughts, etc., etc. Einstein, to his credit, took the time to read it and realized Bose was onto something, and they jointly published it. And that's what led to what's known as the fifth state of matter, Bose-Einstein condensates, and also a branch of mathematics called Bose-Einstein statistics. Well, mathematics within physics, if that makes sense. Okay, so again, the point is, if Einstein hadn't picked up that paper, either we may not have discovered all of this, or we would have waited till it was discovered in the West or in the recognized quarters before we acknowledge it. Okay. Another example is Jocelyn Bell Burnell, or Jocelyn Burnell, as she was then, the discoverer of pulsars within science, known as one of the most significant scientific discoveries in the 20th century. She discovered the first pulsar, and her supervisors and others received a Nobel Prize for it. Now, maybe they thought she was too junior, maybe she was a woman, but the point is, it seems to be who discovers things which seems to carry weight as well as what is being discovered from what we can see. And the final person I'll mention is Jim Gates. Okay, so James Sylvester Gates, he's one of the founding fathers of string theory, an area called supersymmetry. But what I'm particularly impressed with Jim is, and I've met him a few times, is that he developed what are known as, he utilized Adinkra symbols, which are West African symbols, but he used them in his area of theoretical physics research to represent mathematical manipulations in supersymmetry. And the reason why he did that is because I suppose if you was to just read a paper by James Sylvester Gates, you're not necessarily going to know that he's anything to do with African American or anything else. But by leaving those Adinkra symbols, then it means that others who build on his work, he's left an African footprint in that far realms of theoretical physics. Now, on the one hand, it's commendable, but on the other hand, why should he need to do that? These are the questions I have about research. So sometimes we have to think about, are the great minds across the spectrum of humanity truly being harnessed? Is our record of human endeavour an accurate reflection of its contributors? And does knowledge discovery carry equal weight wherever it's discovered? Now, that's what should happen, but of course, we have to be mindful of that in the research landscape. And I should also mention, these are not historical figures. They are still very much around today as well. So I'm not necessarily talking completely about history in the ancient times, for example. Okay, so going back to representation in physics, and in STEM more generally, I was able to work with the Royal Society, sat on their diversity panel for many years, and we were able to look at data across the entire UK, across all institutions over about a 10 to 12-year period. So you can get some really good aggregated data to see what's happening. And this is an example of what you've probably heard of, the attainment gap. So this is one example where it's for qualifiers, STEM qualifiers with a first or 2-1 degree, and then split up amongst ethnicity. It used to be just white and BAME, and it was a lot closer. And we were able to drill down and actually separate all of this into at least more ethnicities. And you can see actually, when you look at Black in particular, that they were significantly lower than the other groups. And even more recently, yes, the trend is upwards like the others, but it's still below, let's say, where even the white demographic started with 10 to 12 years earlier. So this attainment gap, these were stark numbers. And I suppose that's one thing I would say about mathematics. The numbers can really help to bring home things. Sometimes when you're trying to win over hearts and minds, and that's why I stick to the numbers, you can use as many words as you like, but the numbers, especially when you're dealing in this sort of research scientific domain, you can't argue with the numbers. So this led to a raft of initiatives which could help to address this. We can't necessarily drill into all the different whys, but we can certainly do something to try and change that distribution. And within physics, it was about 1.65% of students who enrolled on a physics degree identified as Black or Black heritage, and about less than 1%, 0.76% on a postgraduate program. Okay, so that's what happened within physics. From my point of view, when I looked out at the cohort of physics students, when I was lecturing, and I still do, but when I was lecturing to the first years, I'd look out to see how many are there. And it's a bit like binary numbers, you know? I'm using some maths terms here, like binary numbers, 0, 1, 1, 0 every year. So what I realized though, one, those few students could support me when I do outreach, especially in community outreach. And secondly, when they graduated, they were still useful to the few who were remaining. So that was an old internet meme. Hopefully it's not the same now. But what we used to do was, we invite them in to meet the new undergraduates and so on, until effectively we reached a critical mass of Black physicists, okay? And then around lockdown, we created a website, especially because we were kind of able to meet, at least online, more regularly, and created a website and started to reach out to Black physicists in other places. So we actually realized the ones who came through Imperial, they were the lucky ones at the time because they were part of a cohort, and there were others who were just, in my mind, slightly more isolated. So our sort of key thing was to represent, connect, represent, and inspire. So one of the things was to showcase and highlight Black physicists and in their different fields and what they're doing and so on, to say, yes, we are here, we exist, so to speak. And so we had a very successful Instagram campaign. We then started reaching out across the country. Before any of you sharp-eyed audience say anything, I'm not responsible for the geography of the map. But you get the idea, it was all over the country. And then we also had online discussions around being Black and in physics and what that means, and from different perspectives, and try to give them jazzy titles like the Black body problem and physicists, about women in physics and that sort of thing, Afrophysics, and the other thing, of course, was to make ourselves known to our own community. So we had articles in, for example, the Voice newspaper, because it's important that you have community support if you're really going to increase representation in an area like physics, or maths for that matter, to be fair. But we've also done more serious things and made a collective submission to the government inquiry into equity in STEM, for example, and give a collective voice within that physics space. And we also do things to obviously increase representation. We've got two strong programs. One of them is the Representing Physics, where we work with year 11s and 12s. They spend a day at NPL, National Physical Laboratory, a day at Imperial, a day at the Institute of Physics, for example, and do lots of different activities. We also have something called Amplify. It was in Manchester last year. It was a residential this year in Southampton, and that's for undergraduates. So what we're trying to do is strengthen and support the pipeline at the various stages. And then even moving forward, one thing which was clear is that we sort of know the trajectory up to PhD, but then if you was to say to someone, well, once you've got a PhD, how do you become a lecturer or a professor? It becomes much more murky. I don't know if that's by design, I don't know. But one thing we wanted to do was demystify that. So we worked with the Royal Society to create this research career roadmap, which really opens up all the different career paths and what is required to achieve them. Okay, and then the other thing is, of course, going back to that data, one of the things that came out of it was the career development fellowships for early career researchers, Black researchers. And this comes with funding over 4 years. And if you know about the sort of academic path, getting a fellowship at that stage, it can be quite key to helping to cement your career and establish you as an independent researcher. So we've had the second cohort who've just been, awarded. And so I believe there'll be another one next year as well. So of about 8 students, I should say 8 researchers, sorry, 8 early career researchers. So again, the other thing, we've had summer school for early career researchers, and we've partnered with lots of different organisations. Okay, and this started from, if I think back to when I was doing my PhD, obviously none of this sort of support existed. So I'm hoping that this helps to lay the foundations so that they can rise together, so to speak. Because you know the old Far Eastern saying, that the nail that sticks out is the one that gets the hammer. Maybe you get that one. Anyway, I noticed there was a couple of copies in there. I do encourage people to bring their authentic self into what they do, and I'm no different. So one paper I wrote for Black History Month for Mathematics Today incorporated many things, including EDI, some research around the mathematics and around sampling theory, but also my interest in sound, music, and so on. So again, I sort of go back to that Jim Gates example. Sometimes, as much as you say, well, if I read a paper, they wouldn't know who I am. Sometimes I kind of want to give a hint of who I am, if I can. Why not? Okay. As I said, and similar with Physics World, for example, using analogy, the joy of connecting quantum black dots. And I sort of go on to explain what a quantum dot is and then put it into this context. And also with young people, I'm proud to say I'm one of 2 featured scientists in Stormzy's children's book. So there you go. What to say, really? It's not quite a Stormzy scholarship at Cambridge or anything, but it's a children's book. But also on a slightly more, I suppose, fun side, I was involved in a comedy show called Evil Genius with Russell Kane and some comedians around, and it was about Albert Einstein and whether he was more evil or more genius, depending on a few things they had found out about him, shall we say. But I was still able to contribute some aspects that Albert Einstein had contributed to civil rights. And he was actually the co-chair of the Anti-Lynching Society in America. And this was in the 40s. So, it's quite good to be able to get some of that across. And then I suppose another highlight.
Now, this year's Nobel Prize for Physics has been awarded to 3 scientists for their work to understand complex systems, such as the Earth's climate. The Swedish Academy of Sciences praised the work of Syukuru Manabe and Klaus Hasselmann for their work that helped predict the impact of global warming on the Earth's climate. Giorgio Parisi was recognized for his work on fluctuations in physical systems. Let's get more now from Dr. Mark Richards from the Department of Physics at Imperial College London. Hello to you. Thanks for being with us. Deserved winners?
Absolutely. I think they laid the foundations for understanding, as you said, complex systems, particularly allowing many scientists to start to model the atmosphere and the climate system, which is of course quite complex and full of many components.
So for laymen and for not very bright people like me, just explain roughly what they did.
Well, essentially, as you know, you can't measure everywhere all of the time. If we did, then we'd be able to know exactly what's happening. But in fact, what they did, they laid the foundations so that we can understand, for example, the link between CO2 production and increase in surface temperatures, for example, or the link between surface temperature and atmospheric temperature and human activity. And these are all interconnected complex systems which affect all of us in some way, as well as the entire ecosystem. So to lay the foundations that allow you to model these things so that you can really get an insight, not just to the problems and the interconnectivity between them, but also hopefully towards collectively acting to find solutions.
I mean, how reliable then do you think these models are that they came up with?
Well, I think like anything, models are something that can always improve, and that's what's happened over the years. They've become more and more reliable as more and more data becomes available, especially with the evolution of things like machine learning and so on. We're starting to learn more and more about the atmosphere, and we can model it more and more accurately. But I think it starts from the fact that had they have not laid those foundations, we might have perhaps collectively sort of continued with the way that we were industrializing on a global scale without really paying as much regard to how that can impact on things which seem quite distant on the face of it.
So the practical applications then can be used now?
Absolutely, and they are being used now. And in fact, you know, we've got the climate summit happening very shortly, and in many ways, many of the decision makings. In fact, the IPCC report, which sort of helped to galvanize governments and leaders globally some time ago, was very much underpinned by much of the research and the work that was built from the foundations that were laid by the Nobel Prize winners.
Okay, so again, I suppose part of what I'm saying is that you can use much of your experiences by being versatile to be able to get these opportunities. And I suppose it hasn't gone without being recognised. So Luke mentioned some awards that I've received, and as well, I also received the fellowship at the Institute of Physics. So I didn't set out for awards. I do things for a cause, of course. But I suppose it's nice to be recognised. But the real thing is actually that it helps to amplify what you do, which will help to get others, because many hands make light work, and there's always something we can do. I always used to say to undergraduates, you can be a mentor to school children and so on. If you're a postgraduate, you can help undergraduates, and that's kind of how I see it, because as they say, no one is an island. Okay, and then I suppose I want to draw a quick analogy with some of my experience from atmospheric physics in terms of how this has helped in terms of the sort of equity work that I've done. So, as I said, my PhD was around ozone depletion, and there were these particles called polar stratospheric clouds. So they exist in the stratosphere, and they're ice-like particles, but they're made of nitric acid vapor and water. And what happens is they help to catalyze ozone depletion. So they help make ozone deplete a lot quicker than it otherwise would have. And they wanted to understand, well, how did that happen? And what they realized was that these PSC particles, when they were in the stratosphere, then the ozone would adsorb onto the surface. And then the CFCs, or the chlorofluorocarbons, they would also adsorb onto the surface, and then that's where they would react. Okay? So in other words, the presence of these particles would catalyze the reaction. But they needed to be there so that you can adsorb, and it would happen much quicker than if the CFCs and the ozone was just in the gas phase and you had to rely on a statistical collision in the gas phase. So when I think about developing and founding the Blackett Lab family, I was at Imperial for many years, and I was almost like the polar stratospheric cloud. I was the, if you like, the ice particle that was still there. And then as these students were passing through, they would adsorb, not literally, but they would adsorb, and I would try and engage, connect with them, support them, and so on. And so eventually we reached a sort of critical mass. And now I believe the Black-Iglap family is like the polar stratospheric cloud for black physicists generally, if that makes sense. So in a way, sometimes when we learn things in science, you can always find ways of seeing how they could be applied in other ways. And then the final bits and pieces I'll say is that I do also like to have fun with light and sound. In the interest of time, I won't play you any remixes, but you can check out DJ Chemist on SoundCloud, because I do like to remix things, actually reggae them. But this particular one, don't play it yet, but this was actually, I'm just going to give you an example of when art and science can combine in the most unexpected ways. So I used to have an outreach coordinator called Vanita, who was essentially an artist more than a coordinator. Well, okay, she was an artist mainly. And we had to work on a program with the year of the photon, so it's all to do with light. So we worked with some researchers and they'd explain about different, how you can use light in different ways. And one of the things was to do with polarized light and how you can change color depending if you shine it through a thin film like sellotape, depending on its orientation. And so Benita took that idea and decided to make a piece of artwork by orientating the sellotape behind a white light background. And you only see the image when you look at it through polarized light. Okay. So does anyone want to guess what that image is, by the way?
Street map.
Oh, street map. Okay. Anything else?
I see a face somewhere.
A face somewhere?
I think it might be Gustav Klimt.
Okay. Well, let's have a look through the polarized filter. Okay. You can only see this. If you've got Ray-Bans with P on them, they could work as well. Oh, where are we?
So I'll just show the video, yeah?
Yeah, showing the video, sorry. Oops. Okay, here we go. Let's see if we can freeze it, if we can go back and freeze it, sorry.
So I'm just trying to share it for everyone else watching online.
Ah, oh, there we go. Right.
Maybe from the beginning.
Yeah, play it.
So if you just step one to, yeah, that's all. Just one, this way, please. Thank you.
There we go. Okay. So again, you can see that when science, the scientists by themselves probably wouldn't produce a piece like that. And the artist by herself, without having a little bit of underlying knowledge of science, probably wouldn't have produced a piece like that. That ended up being shown in the Tate Gallery and in Germany and in France and so on. And she's now a professional artist. So, I suppose we were a victim of her success, so to speak. So again, I'm always a big believer that the brain has a logical side and a creative side. Oh, we have to go back to the slides.
Just like it. No,
Yeah. But it was Klimt, right?
It was Klimt. It was inspired by Klimt. You're absolutely right. Yeah. Very good. Very good. But you were closest. Maybe you were studying the lines very carefully. Okay. Okay, actually, this is the summary. So this is a summary of my career journey. I've called it a flavorful summary, steamed rice. Okay. Now, most cultures throughout the world have some kind of steamed rice. We won't talk about, which one's best and all that sort of thing. We won't go there. But why do I call it steamed rice? Well, that steam, science, technology, engineering. Of course, you need arts, mathematics, and of course, that's got to be underpinned by a good education. Okay, but if you do that, then you can engage in research, innovation, culture, and enterprise. So that is why I say my career is steamed rice. I believe that in order to adapt to this ever-changing world, you've got to be versatile, and I keep myself versatile. Almost on purpose. One, because it makes life more interesting, to me anyway, and two, because it also means that you can adapt to wherever you're needed and develop your skill set. So the final thing I'll say is Jim Gates was actually, Abdus Salam is a Nobel Prize laureate in physics, and he was Jim Gates' mentor. So when Jim used to go around to these theoretical physics conferences in the 70s and 80s, there wasn't many people of colour there, and Abdus Salam was very prominent in that field as well. So he sort of took Jim under his wing, and he said something to Jim a long time ago. He said, when enough people of African heritage do physics, they will bring a different aesthetic, and it will be new and valuable. And that's what's lost when people with different inputs don't participate in science. We miss the opportunity to create jazz. So really, that's all I'm trying to do, create a bit of jazz in the physics world. Thank you very much.
Thanks, Mark, for that brilliant talk. There's plenty of time for questions. So any questions in the audience? Nara, you seem to have a question.
I've got one.
Yeah, well, probably just a statement is that you know, you've been a supporter of the Black Heroes of Mathematics Conference a number of times, you know, sitting on a panel twice, and it's you're the first physicist that we've had actually given a talk. So I just want to say thank you very much indeed, and for such an inspiring talk. And we're definitely going to bring you back, but please next time you format a little content.
Oh no, that will be later. I'll do a nice technical talk for you guys.
What has been your most challenging experience in your career?
Ooh, that's a tricky one. Most challenging experience. I would just say managing one's frustrations. You can manage those, that help.
I hear you.
Awesome, Mark. Awesome. What was the surprising thing that you picked up out of the sensor data?
Yeah. Well, I'll tell you one interesting, it wasn't necessarily surprising, but it was an interesting thing to think about the consequences. So, for example, we went on a sort of mapping expedition, if you want to call it that, around South Kensington all the way to Vauxhall and around there, and then came back to Imperial. And we noticed two distinct hotspots at the time. Now, this was quite a few years ago, so I'm not claiming those hotspots exist right now. But back then, they were very distinct pollution hotspots. One was just near Vauxhall Bridge, and that was kind of understandable. There's a lot of traffic flow around Vauxhall Bridge, so I kind of understood that. But the other one was near Harvey Nichols and Harrods. And so I suppose I did a thought experiment to say, well, imagine if there really was a really permanent dangerous pollution hotspot somewhere like Harvey Nichols and Harrods, and you were a local authority. Would you release that information or not? Or how much would you release? Because it can have a lot of effects on different things. That dream penthouse for your young family suddenly becomes a dangerous spot, for example. What does that do to house prices, businesses, etc.? So if you were a local authority, that's an ethical question more than anything else, because really you say you want to be transparent and give the public all the information they need to make the right decisions. But that would be a situation where it could also adversely affect business. So that's just one example which I thought was surprising just by picking up the data. You wouldn't have got that otherwise, if that makes sense, by just looking at aggregated data.
Nice, so we have a question from the Zoom. So Troy Astarte, do you want to say your question?
Yeah, sure. Thank you. You hear me okay?
Yeah.
Okay. So I was really interested in your air pollution monitoring experiments and when you were talking about the different routes and paths that you could take. And I wondered if this would be an opportunity for exploring citizen science, depending on how big and how expensive the sensors are or how small they could get. Maybe they could be, for example, attached to bicycle couriers or something like that. Particularly then, in light of the second part of your talk, thinking about broadening participation and increasing the diversity in science, feels like that could be a really great way to show people that actually you don't even have to be a career scientist to make helpful contributions to science.
I think you're absolutely right. I mean, I must admit, at the time when we developed those systems, they were relatively expensive because they were very high precision optical systems. But with how technology has moved on since then in many different ways, and even in terms of the data and even aspects of AI and machine learning that can actually do a lot of the sort of analysis of the network, I think it is a really, really good idea. And I certainly wouldn't rule it out. I suppose the only thing is there are some relatively hard limits as to the size of these particular sensors. But myself, I'm not even saying that we have to use these specific sensors. I think the idea, there are always different types of sensors being developed over time. So I'm quite willing to, I'm sure you can find the right solution. But the principle of getting ordinary people involved in scientific research, I think is vital, because I'll tell you a term I don't really like, my pet term that I don't like, science and society. Simply because it gives the impression that scientists are not part of society. They're over there doing their science, and then the science happens and they unleash it on society, when in fact society owns the science that we do. They pay for the vast majority of it, and the scientists themselves are also part of society. So again, I think this would be a great example of showing how that collaboration can work.
Okay, so yeah, maybe one final quick question.
Yeah, thank you. I really enjoyed that talk. I have a question about the attainment for Blacks. Are there any ideas or any things that that in academia is going on to change that? Because it's the same across engineering outlets as well. The first and the 2 ones are kind of limited from those communities.
Well, I think generally within that landscape, universities are at least looking at that data now and being more open about it. That's the first stage. So I would take that as a signal that they want to do something about it. Now, as for the nuances as to what's really behind it, that's much more tricky to establish. I mean, the main thing I do is, well, I was a PI of a project called Strengthening Learning Communities. And one of the things which is obviously important is a sense of belonging. And so if you're from an environment, a marginalized community, and you go into, let's say, an elite space, it's not necessarily an environment that you're just naturally used to. And then on top of that, if you're in a discipline where you don't see many people like you in that discipline, so you've got to overcome the sense of belonging to the institution, as well as the sense of belonging to the discipline. Am I really a physicist? Am I really a mathematician, for example? So I try to, a bit like what I showed with the Blackett Lab family, I believe it's about providing support in different ways. I used to speak to some students who have long since graduated, and they told me now that, sometimes they used to come to, when they came to my office, they just came so they could just be themselves. Because we didn't actually talk much about physics, if that makes sense. We just talk about whatever, but the point is they just wanted to be themselves, which now when I look back, means that they almost had to not be their authentic self for most of the time. And anybody knows, even from a music perspective, if you're an artist, and you're trying to record a track, you won't record it if you don't feel comfortable. You won't perform your best if you don't feel comfortable. And so I think that's part of it, making the environment more inclusive and more comfortable, and also doing what we can to sort of enhance that sense of belonging, to really make you feel, not just say it, but actually believe, yeah, I do belong here as much as anyone else.
So I think that's a really apt point to end Q&A for Mark's talk. So let's give Mark a round of applause.